What is an alternating signal?
There are two types of current, and a direct current and an alternating current, right? So alternating current is the one which goes from, like, if you have like I just draw a component here, and so just if you connect a battery with a direct current which is DC, like a resistor, what happens? The current, or even you can call it a signal, will pass only from one side to the other. The current will only flow in one direction, right? So in this component, if I have a resistance, so what happened? The current only flow in from top to bottom. In this circuit, it will flow from that point X to that point Y. Always the current will flow from X to Y. Right? If I connect it the reverse way, I connect the positive on the bottom side and the negative, then current will flow upward from Y to X. Is that right? Do you know this thing? That's why this thing is called a direct current. So current either flows from X to Y or Y to X, it doesn't matter. But if it's not reversing its direction, it's a direct current. But if you connect, instead of that kind of cell, if you connect with that kind of a symbol, then for half cycle, current will flow from X to Y, and for the other half cycle, the current will flow from Y to X. Got it? So current is flowing in this case for both. That's why we call it alternating current or alternating signal. Is it clear?
Can you explain it again?
Okay. Do you know we have two types of current? Like from IGCSE, DC and AC.
Yes, yes.
So that AC is alternating current. And why we call it like DC and AC? Because for DC, no matter you could connect a resistor, I just connect the resistor like this way. So in this case, the current will flow from, I use the top terminal as X and the bottom one as Y. So you can see that the current is flowing from X to Y. Is that right? If you connect the battery in a reverse way, that this terminal is negative and this one is positive, in that case, the current will flow from Y to X. Got it? If that is X and that is Y, current will flow from positive to negative like this. Is that right? But instead of that positive and negative terminal cell, if you have connected to an alternating current source or an alternating signal like this, then for half cycle, for half of the duration of the time, of its time period, it has a time period which we will discuss later in detail. So for half of that cycle, it will flow from X to Y. For the other half, it flows from Y to X. So it, in that resistance, it's keep reversing its direction all the time, alternating its direction, altering its direction. That's why it's called an alternating current. Got it?
Yes.
So that wavy thing which they have drawn in the symbol is actually a representation of an alternating current. Is that right? Is it clear?
Yes.
Okay, that's good. What next? Any other symbol?
I'm familiar with the rest.
Okay, that's good. Okay, so as we move on forward, so have a look what we have. So after this thing, what next we are going to practice is like conductors and insulators. You have mentioned a conductor is the one which allows the current to pass, and an insulator is one which do not allow the current to pass. conductors are metal, and other things are like wood, plastic, ceramics, they are insulated. That's good. But do you know what makes a metal a conductor, or what makes a conductor or a good conductor?
The conductors have free electrons.
That's very good. And do you have an idea what free electrons are actually?
Like free flowing electrons.
Not
They're
all
not like
electrons
bound.
are, so that's good, but I want to make it very sure that you have a good idea. Not all the electrons are freely moving in orbits, like around the atoms, continuously moving. None of the electron is like stuck at one point. They are moving around the nucleus in an orbit.
Yes.
Then what's special about the free electron?
I'm not sure.
Okay, so just a second, have a look. Say that this is a nucleus, and around the nucleus what we have these orbits. Do you know a little bit chemistry?
Yes.
Okay, in that chemistry, just a second. So do you know the atomic number for sodium atom?
I think it's 11.
It is 11. And do you know the mass number? It's 23. So why I'm discussing it? Because we need to know a few things. We need to discuss how many protons are there and how many neutrons are there. So the number of protons is 11. And do you know that if its mass number is 23, the number of neutron is 12. Is that right?
Yes.
So how many electrons shall we have?
11.
That's right. Can you tell me how many electron in the first orbit, how many electron in the second orbit, how many electron in the third orbit?
There's 2 in the first orbit.
That's right. How many in the next?
And there's 8.
That's right. There are
And then 1 in the third orbit.
one in the last one. That's right. Out of these 11 electrons, how many are bound and how many are free?
Aren't they all free?
No. Not all of them are free. Only one is free, not all. I will let you know why. Because this is really important to understand, especially some concepts in like 1 or 2 concepts in AS, but few concepts in A2. It's really important to understand this thing. So electrons, I do write it here. So we have electrons which are moving in the orbits. So 2 in the first orbit, 8 in the next orbit, and 1 in the last orbit. When we discuss this thing, and this atom is neutral, it has 1 free electron and it is neutral. Why it's neutral? Although it has 1 free electron, because that free electron is not an extra electron, it is the 11th electron. Free electron is never an extra electron. Extra electrons are something different. Accepting an extra electron or donating its own electron is something different. Free electron is not, and don't mix it with an extra or excess electron. It's the 11th electron for 11 protons. Got it?
Yeah.
Is that right? Okay. Now, I want to show this thing, but this is a large view. I want to show this thing on a smaller scale, because I don't want to show one atom, I want to show a lot of atoms. So I just copy the same thing and I'm going to pack something, the same figure, into a smaller version. I don't need this thing and I don't need this thing, but the rest of the figure I'm going to pack it. So this figure is just one part, because the 11th electron is actually the free electron. Just fit on, I can adjust two things here. I can adjust the writing. So this thing is there. Is that right? This thing is there. What about this 11th electron? That's also there. But how? This orbit is not an ordinary orbit. This orbit is not going to be an ordinary orbit. Because when we place many atoms together, this particular one is going to overlap. So we show it with different. So I show it with pinkish color, one of the things, and other thing I'm going to make it a slightly dim. So this 11th electron is here. So still you can see that this atom is what? This atom is neutral, is right?
Yeah.
But when I talk about a sodium, like a strip, will it have only one electron in it, or will it have a lot of electrons in it? Oh, sorry, one atom in it, or a lot of atoms in it?
A lot of atoms.
That's right. So we are going to stack these atoms together. So when we stack these atoms together, what happens? They get stacked like this. So that's how they get stacked together. Alright? So they keep getting stacked like this, more and more. So what's happening? Look at the highlighted orbit. Isn't it overlapping?
Yeah.
So this is what make this 11th electron a free electron. This what makes this 11th electron a free electron. How this one is a free electron? I just wait a minute. I just make it down as well. So this is one strip, like one layer of atoms in the strip. We have another layer of atoms at the bottom, and so on and so on. Right, like this. So how many protons are there in every single atom? That many electrons are there in every single atom. Is that right? And all the electrons are moving in the orbit. The 10 inner electron and this outer electron as well. But those 10 inner electrons are like bound. How they are bound? They are bound to just turn within that nucleus. Got it?
Yeah.
But what's special about this 11th electron? It has a path. It can flow from this orbit and it can go to the next. Got it? As it goes to the next, so what happens? The other electron comes to this one. Just wait on it. So this electron goes to the next. So this electron goes to some. Okay, I started from for a reason. I just started from the other side. Say that this electron comes this way. So what happened? This electron goes somewhere else. So this electron goes somewhere else. And this electron goes somewhere else. Got it? So that's how they keep moving. Because what the nucleus will, every atom will allow only 11 electrons. None of the atom will allow the 12th electron in its orbit. So as it gets one electron, it loses one electron. So in total, each atom has 11 protons and 11 electrons at all. But this outer electron, which is in the pink orbit, only that has a freedom to switch its orbit. It can move from one particular nucleus to another nucleus. All other are just, they are moving, but they are bound to move with around that nucleus. Got it? But that electron which is outside, it can go anywhere in the whole metal, following these orbits. Got it? Yeah. The electron in these third orbit, the 11th electron of each sodium atom is free to move anywhere. Got it?
Yeah.
So this electron is free. All other are bound to just, they cannot switch their nucleus. They cannot switch their atom. Is that clear?
Yeah.
So this thing is always there. Now what happened next? So right now, these are free electron, they are moving in random direction, nothing is there, but when you connect one side of this sodium metal strip with a positive terminal and other side of this sodium atom with a negative terminal, then what's gonna happen? Then these new electron gets a force. Right now they are free, but if you put a positive terminal on the left side and a negative terminal on the right side. So I show that I will keep in my discussion, I will try to keep it like that. I will always use a positive red color for the positive thing. Just like in this figure, you can see that inner nucleus is red. Why? To show it positive. Got it? So on one side we connect with this sodium strip with a positive like electrode, and on other side we connect it with a negative electrode. I make it blue in a moment. So on the other side we connect it with a negative electrode. So what do you think? This negative, will it attract the electrons or repel the electrons? The negative terminal, the blue terminal, will it attract the electrons or repel the electrons?
Yeah.
Similar charges, do they attract or repel?
Oh no, they will repel. They will repel.
So we have connected the blue side with the negative terminal and the red side of this sodium strip with a positive terminal. So all these electrons now get a movement. So they move from here to here. As this atom gets an electron, its electron goes to the next. Only the 11th outermost electron which is free to move, not the inner electrons. Got it? So now earlier I have shown you it was moving randomly, but now they will not move randomly. Why? Because they are being pushed, is right, by the electric field, right? So they will start to move in a particular direction. Is that right? So all of these electrons start moving from left to right. Sorry, from right to left in this case. Got it? All these electrons start moving. Remember, their movement is not a straight line still. They have to stay within these orbits. So they move in a very particular way, like within the orbit, like goes like this or like this. But overall, they are shifting from left to right. Got it? Oh, sorry, from right to left, from negative to positive. Got it? They will stay within the orbit and like that. Why? Because no doubt they can move, but when they are moving, there are chances that they hit this static thing in the middle, which is not moving, the whole positive nucleus and even the bound electrons. So when a free electron hit this thing is heavy. So it bounces back and goes and switch its path. If it hit it again, it will turn. So only the free path is in between. The pink line is a free path. If they try to find any other path, they will strike the atom. Got it? They can only move without hitting the atom. They can only move in these pink orbital things. Got it? So they still keep moving in the orbit, but they can move from right to left, from negative to positive. Is that right? Is that right? So say that all the free electrons, they get shifted here. All the free electron get repelled from the negative side and attracted by the positive terminal. So they get shifted here. Got it? that right? All the free electrons get this. Is that right? All these electrons get shifted here. Why? Because positive is attracting it. Negative is repelling it. Got it?
Yeah.
Okay. Now, do you know what's the job of a battery? Look at the terminal. Which terminal it is connected with the battery? This red side is connected with which terminal of the battery?
Positive.
So yes, all these electrons can move toward that positive terminal of the battery, right? And the job of the battery is to push. We will discuss it in more detail later. The job of the battery is to push these electrons from positive to negative terminal, right? So all these electrons which we have shown here, what will happen? They will get shifted toward I just packed them and I will so they will get attracted toward the positive terminal of the battery, and once they reach the positive terminal, then what happens? Then the battery pushes these electrons and supplies them energy and push them toward this side, right? So as those electrons goes there, passing through the battery, negative terminal again start pushing them away from the battery. Is that right? So I just first show one electron. So what happened? As this one electron reaches the battery, battery pushes it from the positive to negative, and this again start running here, right? So that's how they keep running throughout the circuit, and they will again refill. They have moved, and each of them will get shifted back. So that's how they keep moving. Every single electron goes here, and from the circuit flows back and then back to this system. Got it? So that's how these electrons keep moving, right? So, but what's the difference? Now they are moving in a particular direction, right? Right now they are moving in a particular direction. Is that right? So that's the free electron. Only the electron in the pink or the last orbit, that's the free electron. Got it?
Yes.
Okay. So these free electrons, while they are moving, there are quite a lot of chances that they strike the atoms. Remember, why? Because right now it looks okay. They can move easily through the pink orbits, and they cannot. There is no chances that they collide the atoms. Yes, right now in this setup there is no chance they will collide the atom because they can have free paths, right? They can easily move from here. But do you know what atoms are doing in a solid? In a solid, what atoms are doing? Do you have an idea? They are vibrating, isn't it? Atoms are vibrating. Do you know in solid atoms are fixed and they can only vibrate?
Yes.
So when this atom, I just show one atom as vibrating. So when this particular atom is vibrating, so isn't the chances of collision when the electron tries to pass through this region, isn't there a chance of collision with the atom because atom is vibrating? So atom may be here.
Yes.
So yes, that's what is the resistance. So when this atom goes in the path and hit this particular electron, even in the free orbit or in the bottom one, so there is chances of collision. And as much they vibrate, what happened? As much will be the chances of collision. If they vibrate less, there is less chances of collision. If they vibrate more, there is more chances of collision. Is that right? Is that right?
Yes.
So due to that collision, what happens? Resistance. Because what is current? The flow of charges. Those free electrons are moving freely, but during their motion, during their flow, if they collide with the atoms, their flow get enhanced or slow down or like repelled. What happened to their flow? It gets hindered. Is that right? Is that right? So this hindrance due to the collision of the electrons, free electrons with the atoms, or we call this structure thing, because actually not together, but this structure thing, in the chemistry you use a word called lattice. Are you familiar with that?
Yes.
So these atoms, the particular atoms in the middle, are aligned in a lattice. I just draw it quickly. So this thing is aligned in this structure which I'm going to draw is actually a lattice. Just wait out. So this thing which we are going to draw is so this whole thing is a lattice. So what happened? This lattice can make collisions with the atoms, right? Oh, sorry, with the free moving electrons. This lattice, okay, call it lattice. So this can be, this is the reason, collision of the electrons with the atoms in the lattice causes resistance. More the collision, more the resistance. Less the collision, less the resistance. And that collision is due to vibration. And what you think, when you increase the temperature, what happened to the vibration? Will they vibrate more or will they vibrate less? When you increase the temperature.
They will vibrate more.
So if they vibrate more, what will happen to the chances of collision?
Increase.
So what will happen to the resistance?
Increase.
That's what it is. Increasing temperature increases the resistance. Got it? The term
Yes.
you have to use, the cause of the resistance is the collision of free electrons with the atoms of the lattice. Is that right? Is it clear?
Yeah.
So what we have discussed, the free, first of all, we have discussed the free electron thing. So what are the free electron thing? The free electrons are the electrons in the outermost orbit. They can never be the inner orbit electron. Free electrons are always in the outermost orbit. Outermost orbit, which are not bound to any particular nucleus. So it is really important. They are not the atom electrons which are outside the orbit. They are always in orbits. They are always in the pink region. Pink region is the third orbit. But what's the freedom? They can switch their nucleus. Got it? They are not bound to any particular nucleus. But what about all other electrons? They are moving, they are orbiting, but they can never switch their nucleus. Got it? Is it clear? This is the free
Yes.
electron thing which I've written. Okay, the next thing which I'm going to write is resistance, the origin of resistance. So what's the origin of the resistance? Collision of electrons, collision of free electrons with the atoms in the lattice. And what points we have discussed? Increasing temperature, increases vibration, increases the temperature. Oh, sorry, increases the resistance, increases number of, increases or increases. Okay, I write. Increases probability of collision, probability of collision of the free electrons. With the lattice atoms. So what happens? It increases the resistance. Got it? Is that part clear?
Yes.
So what we have written at the bottom, read these lines. If there's any problem with this thing, you can ask. Clear about this part?
Yes. Clear.
Okay, that's good. So when we move to the next thing now, after this free electrons, there is a topic which they have discussed it, but I will discuss that topic a little later. Electrons are the charge carriers. Free electrons are the charge carrier in the case of the conductors. Okay. If I ask you to draw a simplest circuit to light up a lamp, what you will draw? You can draw. You can use the tool, drawing tools, annotation from the Can you draw on this board? That's very good. Can you let me know how many components you have used? In this diagram or in this circuit, how many components you have used?
Two. The battery and the lamp.
Okay. The battery and the lamp. Think again. Is there any extra thing other than the battery and the lamp?
The connecting wire.
Yes. They are important. They are the part of that thing. Got it? So yes, you have drawn it very good. That's the right one. I draw it again. Just a second. So you have used a battery. What is it? Just a second. So the components you have used is one is the battery, which can be shown with this thing. The other is the lamp, which can be shown with this thing. So this is lamp and battery. To make the circuit work, we need the connecting wires. Got it? We need the connecting. Is it clear? So can you let me know what's the purpose? Why you use a cell or a battery? Why you use a lamp? And why we use connecting wires? The purpose of each of these in the circuit.
The battery is the source of the power, and the connecting wires to help with the flow of electricity, and the lamp is to like for brightness.
Okay, your answers are actually right, but here we have to talk technical. And what's that? Power is a different thing. No doubt battery is a source of power, but actually battery supplies energy. Energy supplied by the battery per unit time is power, but what battery supplies? Battery supplies energy. Got it? Battery converts chemical energy. Battery has a storage of chemical energy and converts it into electrical energy. That's right. That's the job of the cell. So what does cell do? Converts electrical energy into chemical energy into electrical energy. Is that right? Now, you can use the same kind of idea as I have used for cell to explain lamp. What lamp is doing?
The lamp converts electrical energy into light energy.
That's very good. What the wires are doing? What's the job of the wires?
The wires carry the electrical energy, like they help flow.
Okay, that's right. But explain how. Like it's the same thing, like you say that roads transfers the goods, like the luggage. You have to transfer luggage from one city to another city. Is it, and you use the roads, but is it really the roads which transfers the luggage to the other city?
No,
What transfers your luggage to the other city?
like the vehicle.
That's right. In this case, the vehicles are the free electrons. So we use metallic wires. We don't just use any wire. We use metallic wire. Why we use metallic wire? Because they have a lot of those struck, which are the electrons. Got it? So what wires do? We use metallic wires. And why we use metallic wires? They provide us a lot of free electrons. Why free electrons are important? Because free electrons are our trucks to carry that energy from the cell to the lab. Got it?
Yes.
So wire, what we use metallic wires. Wires provide free electrons and the passage for the flow of those electrons. Got it? Wires provides free electron which carry energy or electrical energy from cell to lab. Got it?
Yeah.
And what lamp use? Lamp use the energy or electrons?
The
What?
energy.
That's right. Lamp do not use the electron. Lamp do not consume the electron. Lamp only consumes the energy and let the electron flow. Like the luggage, the trucks which transfer your luggage, you just unload luggage at your home and let the truck go for the next journey. Got it? Same happens here. Electrons flow in this circuit. How they flow in the circuit? They start their journey from the negative terminal and they continue and they reaches the lamp where they actually unloads the energy, not the luggage. Here our luggage is actually the energy. So they unload their energy at so just a second please, I just use this thing and just so this thing is red thing. Actually remember, red thing shows energy. Okay, this electron is energetic. Okay, this electron is energetic. What happens? The negative terminal of the battery repels it and it flows from here to here. And when it reaches the battery, lamp only consumes and radiate out the red energy. I use the red color just a moment. Lamp radiates the energy and let the electron go. But there is a difference. I show it with like blue color. What is that blue color means? That now it have no energy. Got it? But whether it has energy or not, what's the charge on the electron? Whether electron has energy or not, electron is negatively
Negative.
charged particle. So what you think? What the positive terminal of the battery will do? Attract it or repel it?
Attract.
So this, like out of energy or exhausted electron, continue to travel and reaches the positive terminal of the battery. And what's the job of the battery? To supply energy. To supply energy to what? To these electrons. So battery again supply this energy to the electron and electron get energetic. Got it? So battery
Yeah.
supplies the energy to the electron. Lamp also there's energy transfer taking place at the 2 point. There is an energy transfer taking place at the cell and there is an energy transfer taking place at the lamp. Is right? So I have just shown it like an electron, but remember, it's not an electron. Call it a bunch of electrons. This circle thing is a bunch of electrons. Got it? Red circle means energetic bunch of electron. Blue circle means less energetic or exhausted electrons. Got it? So why I turn that one electron into a bunch of electron? Because when I want to discuss it, I need to discuss 1 coulomb of electrons. Say that this thing is 1 coulomb of negatively charged electron. So this thing is 1 coulomb of negatively charged electron. And this thing is 1 coulomb of negatively charged electron. And this thing is also 1 coulomb. Got it? So 1 coulomb is a not single electron, it's a bunch of electron. It's a lot of number of electron, which we will practice sometime later. But this circle contains a lot of electrons. Got it?
Yes.
Which makes 1 coulomb. So there are energy transfer taking place at the cell, and there are energy transfer taking place at the lamp. So this 1 coulomb means per coulomb. Per coulomb, coulomb is the unit of the charge. So 1 coulomb is actually per unit of charge. Right? So what is 1 coulomb then? 1 coulomb, just 1 coulomb can be written as per unit charge. Is that right? Can I write 1 coulomb as per unit charge?
Yes.
So there is a term which we are going to discuss right now. So as it gets transferred, we have discussed that energy transferred per unit charge. So as this circle 1 coulomb per unit charge passes through that battery or passes through the cell, there is an energy transfer taking place. So that energy transfer is called, we define it as voltage. I write it clearly. We define this thing as voltage. What is voltage? It's the energy transferred per unit charge. It's energy transferred as that 1 coulomb of electron passes through the cell or lamp. So that energy transferred per unit charge is voltage. I have used voltage. It can be potential difference, it can be EMF, that's a different thing. But this thing, what I have written, is energy transferred per unit charge. Is it clear?
Yes.
Okay. I need this figure. I just move that figure down. Like we have mentioned, we have clearly shown that it's happening at 2 points. So, can you explain what's the difference in the energy transfer per unit charge which is taking place at the cell, and what's the difference which is the energy transferred taking place at the lamp? There is a small difference. Can you identify that difference? There is a small difference. Can you identify that difference? It's 2, and at the cell it's by. Is it clear? Cell
Can you explain?
supplies energy or transfer energy to the charge. Is right? Whereas at the lamp, energy is transferred by the charge. Got it? As an electron
Yes.
is, that bunch of electron is passing, so as they passes through the battery provides them energy, right? Battery provides those charges energy, so energy is transferred to the charge, to that 1 coulomb of charge, to that per unit charge. Got it?
Yeah.
But when the same per unit charge passes through that lamp, so what happens? Energy is transferred by that charge. Got it?
Yeah.
Just withdraw this. So is that clear?
Yeah.
So otherwise, whether it's to or by, it's the same thing. It is voltage. That's why it will be measured in volts. This voltage definition, energy transfer, remember not to represent the energy in this topic with symbol E, because you will get confused with the EMF or you will get confused with the energy. Remember, from work energy principle, work done is equal to energy transferred. That's why we are going to write energy as the symbol W. Why W? Because work done is equal to energy transferred. Is that right?
Yeah.
Just a second, please. So it is work done per unit charge. Got it? So work done is made in joule and charge is made in coulomb. So this thing has a unit of joule per coulomb, right? So this thing has a unit of joule. Work done is made, or energy transfer is made in joules, and the charge is made in coulombs. So joule per coulomb, which is actually equal to volts. The difference between the V on the left and the V on the right, in the symbol the V represents the volts, in the quantities the V represents the voltage. Got it?
Yeah.
Just a second, please. So we will discuss the EMF in more detail, like an extra detail later, but right now I just remember. So although energy transferred to per unit charge by the battery is EMF, but why we need that energy? Because if we don't supply that energy, we have discussed what happened. So we have mentioned what's the battery, what battery was doing. All the electrons, when once they move toward the positive terminal and they get collected at the positive terminal, battery pushes those electrons to the negative side, from the positive terminal to negative side. Is right? Battery pushes these electrons from the negative positive terminal to negative terminal. Is that right? And make them energetic electrons. Is that right?
Yeah.
So that's what battery is doing. So as long as the battery has the energy to push them, as long as the battery has the energy to push them, these electrons keep moving in the circuit and current flowing in the circuit. Is that right?
Yes.
But once it gets exhausted, will battery be able to push more electrons if it gets exhausted of energy?
No.
That's what when we say our battery ran out of energy, right? So battery has no more energy, electrons are still there, but those electrons cannot move toward the negative side and they will not flow back in the circuit to complete the path. Otherwise, as long as the battery has the energy, it absorbs that energy and flow in the circuit and comes back this way. The like charges again, like what the cell again provides its energy and it's again ready to flow in the circuit. So as long as the cell keeps supplying the energy, keep pushing those electrons from the negative positive to negative terminal, those electrons keep flowing in the circuit. But once cell get exhausted, they get stuck here. Got it? If they don't go the other side, they will not move in the circuit. Got it? So this energy is required so that electron can make a complete round trip in the circuit. If we don't supply that energy, they are not able to make a complete round trip in the circuit. Is it clear?
Yes.
So this is why the energy supplied to the charges by the battery to make the electrons go in a complete round trip, it has a weird name, EMF. It is energy transferred to per unit charge, but we call it force. Look, the quantity is energy transferred per unit charge, but we call it as EMF. Why EMF? Because this energy transfer per unit charge is required to keep the electron moving. So the thing which keeps the electron moving is called electromotive force. Got it? The thing or the energy which keeps the electron moving, that thing is called electromotive force. So this is the energy transferred to per unit charge, and why we supply that energy transferred to per unit charge, so that they can complete a round trip. To complete right? So that factor which makes the electron to go around to make a complete round trip, that factor is actually the force behind the electron which it keep moving. That's why the name electromotive force. But technically, still, what it is, it's the energy transferred per unit charge, isn't it? Still, it's written the same thing. It's the energy transferred to per unit charge. It's joule per coulomb. It is volts. It's not Newton. It is. So electromotive force is just the name, because that's the factor which keeps the electron moving. But technically, it is the energy transferred to per unit charge. So it is joule per coulomb. So it is volts. Got it? So electromotive force is measured in not Newton, only the behavior, only the reason what it does is the reason to give it name electromotive force, but otherwise it is volts. It's measured in volts. Why? Because it's still joule per coulomb, not Newton. Got it?
Yes.
The only reason is the job what it does. To keep the electron moving, the force which we need to keep the electron moving is the electromotive force. But to keep the electron moving, we need to supply energy to every coulomb of electron. so that they can make a complete round trip. So that's why we call this. So it is the voltage, but this voltage which is required to keep the electron moving around the circuit, we call it electromotive force. Got it clear? What electromotive force is?
Yes.
So the energy lost, because this energy is lost by the charges when energy transferred by the charge. So not to the charge, when energy is transferred by the charge, so its energy will decrease. So as its energy decreases, what happens? It's a drop, and a drop in what? Voltage. Voltage is sometimes given name as potential. So that's why this thing is called a potential drop, right? How much potential or how much energy is dropped, right? And it's still the same thing. It is measured in volts. Why? Because it's still the energy transferred per unit charge. Energy is transferred in joule, per unit charge is coulombs, right? So whether it's potential drop, whether it's electromotive force, or whether it's just voltage, it's the measured in volts. So actually these two things, whether we call it electromotive force or whether we call it potential drop or potential difference, these two things technically what they are energy transferred per unit charge, whether to or by, it doesn't matter. So that's why both of these things are voltage. That's why both of these things are measured in volts. Got it? Okay, now the next thing, how you define current.
It's the flow of electron.
Okay, flow of electron is no doubt electricity. We have electricity, flow of electron is electricity, but remember, current is a quantity, a measurable quantity. How are you going to measure that quantity? It's the flow of electron per unit time. How many electron flows in 1 second? Only that many electrons or that much charge which flows in 1 second. So we define it as current, rate of flow of charge or amount of charge flow in 1 second. Got it? So we call it as rate of flow of charge. And what it means? Amount of charge flow in 1 second. Rate of flow of charge, not just flow of charge, because if you measure the flow of charge, the answer is in coulomb, and the quantity you measured in coulomb is the charge, not the current. Current is not measured in coulomb. Got it? So if you just measure the flow of charge like 5 coulomb flows or 10 coulomb flows or 20 coulomb flows, that measured in coulombs. So coulomb is the charge, but when you say 5 coulomb per second, that's what current. Coulomb per second is the ampere. So rate of flow of charge, or you call it amount of charge flow per unit time, that what is the current. Got it? So the quantity current is represented with symbol I. Remember, current is represented with symbol I. And the charge is represented with symbol Q. And the time is represented with symbol T. That's why when you measure it, whether capital Q or like small q, I will let you know why I use the capital Q here, but it's measured in coulomb. Time is measured in second. So this coulomb per second thing is ampere, which is A. That's why current is measured in ampere. Is that right?
Yes.
Okay. Just a second, please. I check the text. Actually, the next topic. Okay. Next topic is quite important. Okay, okay. There are like two things. And do you like you said that you practice some questions from topicals? If you have practiced some topical question and you have had some problem in any of the previous questions, do you have it in mind right now, or do you have a copy or a booklet where you find some problems?
Not right now.
Okay. Because I want the other two students, somehow they are not in the class, but this is like basics. Although it has its own importance, but the next topic is a little more like a complicated one. Okay, is it okay if I practice some questions from like the previous part, like the dynamics, like the mechanics parts, work, power, energy, kinematics, dynamic, with you right now?
Yes.
Okay, that's good. I just thank you for that. I just upload a paper, like just. So can you see it?
Yes.
So whenever they simply write a definition for one word, 1 mark, you can always write the formula, but appropriate formula for it. So can you answer the first part?
Work is the force into displacement.
Okay, that's right. But you need to define which displacement.
In direction of force.
Yes, you need. You know it, but if you don't write it, you will not get the mark. Got it? So you have to write it. Force times the displacement in the direction of force. Got it? So use this definition just like I was writing the units, right? Use this definition in your unit, like in your answer part B, to answer what are the unit for the power. Do you know the formula for the power?
Energy over time.
Okay, that's right. But any other? Because they said use your answer of the A. Energy is the same thing as work done. Got it? So power is work done per unit time. Is that right? So they said, because if they have not said, then it's okay. But they have said use the answer to A. So what we have written, what is work equals to? Force times displacement. So do you know the SI base unit for force? It's the SI unit, not the base. So do you know what base? What's the formula for the force? Do you know the formula for force? Any formula for the force?
Mass into acceleration.
So Newton is the unit of the force, no doubt, but its base unit is kilogram meter per second square. Got it? So you write kilogram meter per second square for the force. Then you write meter for the displacement. Then you write second for the time. Got it? So what will be your final answer?
Welcome.
Walaikum salam. Okay, so you are quite late. Okay, no problem with that. We are just practicing some questions. You can continue with that, Tanya. Fatma, what you will get your final answer if you solve all this? If you solve everything, what you will get? Am I audible, Fatma?
I don't think you can simplify this.
Yeah, no need to simplify it, but will not meter and meter get multiplied and give you meter square?
Yes.
Like that. So you will get kilogram meter square, second square into second give you second cube per second cube. Is that right? that right?
Yes.
Okay, that's good. Now read the C part. Like Tanya, we have practiced what is work, force times the displacement in the direction of the force, and the unit for the power, choosing the answer to A. So power is energy transfer per unit time, or work done per unit time. So work is using the answer of the A is force times the distance. So force as a unit of Newton, which is actually kg meter per second as the base unit. So the base unit of the Newton is, or the force is kg meter. SI base unit is kg meter per second. Base unit. So we use that kg meter per second square as the Newton, multiplied with the distance, which is the meter, divided by another second, gives you kilogram meter square per second cube. Got it? Okay, so now they have given everything. They have given you everything. You can find the answer of the B. For the moment, for the calculation of the V, you don't need to worry about this thing, because I have not yet practiced this thing intentionally with you. I will discuss it as a last topic. So just use the above formula and let me know what answer you will get for V. That's right. Okay. There is a small issue. You have to take cube root. Can you check your answer again, please? There is a small difference in the decimal point. Oh, that my mistake. That's actually right. That's actually right. What you have worked out is right. Tanya, waiting for your answer. You have the p value. Convert it into watts. So it will be 84,000 watt. And you have the b value. Using this formula to work out your V. So V cube, first of all, V cube will be equal to P over B, and then V will be equal to cube root of P over B. Can you do that?
Yes.
Okay, do it and let me know the answer. Fatma, we will not do the next part because yet I have not discussed the uncertainty with you intentionally. Why? Because uncertainty is in calculation. So once you are like okay with the calculation of the all AS physics questions, then we will put emphasis on how to calculate the uncertainties. Okay, so first get familiar with the calculations, then we will practice uncertainty in calculations. Tanya, what answer you get for the B? Tanya, still waiting for your answer.
Sir, what do I do with the plus minus 7%?
I said I have outlined it that not to worry about it because we are not calculating the uncertainties.
Okay, so just 0.56?
Yes, both 84,000 and 0.56. Using these values here, check out what you get. Because the uncertainties are there in the next part, which we are not going to practice right now.
I'm getting 53.13.
That's right. Okay. Like Fatma, we are going just because Tanya has joined, and it's good to sometimes revise the things. So what I'm going to do, I'm going to just revise what we have practiced today. Okay, a quick review. Is that fine with you?
Yes. Fine.
Okay, that's good. So Tanya, we have started the new topic that is about electricity, right? And we have just discussed. It's a little more. We have spent a time on this little figure, but we have just otherwise we have just discussed very small thing. So the this first, can you check these symbols and let me know if you are not familiar with any of these symbols. If I will explain why that symbol is like that, or why that's this thing, what is this thing?
No, I know these symbols.
Okay, you know these symbols, that's good. So the next thing we have started practicing is like what idea you have about the free electron? Do you know something about free electrons? Tanya, keep yourself unmute because we are discussing it with just with.
Yes, electrons, the number of electrons in an atom are equal to the number of protons.
But what are the free electrons? This is a sodium atom. It has 11 protons and 11 electrons, right? 2 in the first orbit, 8 in the second orbit.
Free,
Yes.
free electrons are electrons that are not in the orbit of an atom.
Actually, they are still in an orbit of an atom, but they are not the property of an atom. How I will explain it. So this 11 sodium atom has 11 protons and 11 electrons. So the 11th electron is in the third shell. Is right? If you write the sodium configuration, you will not say that the 11th electron is not in the third shell. Is right? It's in the third orbit, third shell. Is that right? You write it as, if you write the sodium configuration, will not you write it as KLM? In K we have 2,
Yes.
in L we have, so it's in the orbit. Although that third electron in the M orbit is the free one, we will discuss why it's free, but it never means it's not in this orbit. It is still in the orbit. But what makes it free? It's not that it's not the in the orbit that makes it free. It's something else which makes it free. So we just combined this figure and we presented this figure in a smaller, like compact view. This one. And the next page is exactly okay. I have to pick one of these. Just don't. Okay, just give me a second. I pick one of these and then I will explain it. Okay, just don't.
I think that's it.
So so this is the thing which we have, and I will just explain it on the previous page. So this thing which I have drawn is exactly the same atom. This thing is exactly the same atom, but I have drawn the third orbit with the pink color. It's a just minimized figure, but the third orbit I have drawn with the pink color, right? So what is there? It's the same thing. You can see that it has 11 proton in the center and 2 electron in the first orbit, 8 electron in the second orbit, and 11th electron is in the third orbit. Is that right? So it is actually the same thing, but in a miniature view, right? So it's the same sodium atom, which has 11 protons and 11 electrons. Is that right? It's a neutral atom. Tanya, is that right? Tanya, are you there? Tanya, are you there?
Yes.
Okay. So we have combined these smaller miniature view to make a sodium metal strip. So a sodium metal strip has lot of free electrons. Each sodium at a lot of sodium atoms, and each sodium atom has one electron in the third orbit, which is shown with the pink. So now what happens? Every atom has those 10 electrons which are just bound to orbit particular atom. They are the inner electrons are just able to turn around that particular nucleus. Can you see it? They only turn around that particular nucleus. Is that right, Tanya? They are bound. They cannot leave this particular nucleus. All those 10 electrons are bound. They cannot leave this particular nucleus. But what about the 11th electron? That, look at its orbit, the pink orbit. Isn't the pink orbit overlapping with the other orbits? Isn't every pink orbit? So this electron stay in that pink orbit, but can go anywhere. That's what we call it free. So they will stay, no matter to which atom it goes, it will stay in its orbit, but no atom at any moment can have 12 electrons. So if it gains one, it loses the one to the other. Got it? So that's how they keep moving. So they keep moving in the pink orbit. So every electron in this third orbit is like having a possibility to switch its atom, but it will stay in the third orbit. No matter where it goes, it will stay in the third orbit. Got it?
Yes.
So that's what we have free electrons. So they are moving randomly. But if we connect the left side of this page, this sodium metal strips, all the sodium atoms are connected in a strip. If we connect the left side with a positive terminal and the right side with a negative terminal, then these free electrons will not move randomly. They get a push. They get a push from the negative side toward the positive side. So all these electrons, they will flow from the negative side to positive side. And remember, right now, it looks okay that they will move straight. No problem with that. No doubt, it's right. No problem there with that. They can move like this. Staying in the pink orbit, they can go like this. But do you know what atoms are doing? The electrons are orbiting, but what atoms or the nucleus are doing? Are they static? Or are they vibrating? the nucleus in a like solid atoms of a solid, what kind of motion do they have? Tanya, atoms of a solid, what kind of motion do they have? They are vibrating.
Yes.
So if they are vibrating, what happens? Will not, there is a possibility that the electron which was flowing freely, if that atom is vibrating, isn't it there is a chance of collision here if the atom is vibrating?
Yes.
So that makes the resistance. So when electrons collides with the vibrating atoms, this slows down, their flow get hindered, their flow get obstacled. So that obstacle in the flow, or that hindrance in the flow of electron, is the resistance. So what are free electrons? Free electrons are the electrons in outermost orbit which are not bound to any particular nucleus. They can switch their nucleus, but to whichever nucleus they will go, they will still be the outermost electron. Got it? To whichever nucleus they go, they will still be the outermost electron in the pink orbit. Got it?
Okay.
You can't disturb the
Yes.
inner structure. They are the bound electrons. So that makes it free electron, and so that's why they can move freely. So what happened? The collision of free electron with the atoms in the lattice, this black line mesh-like thing is called the lattice, the arrangement in which atoms are placed. That arrangement has a name called lattice. So what happened? When we increase the temperature, the lattice vibration increases. When lattice vibration increases, the probability of collision increases. When the probability of collision increases, the flow gets restricted and resistance increases. Got it? What we have written at the bottom? Tanya, is that okay? Okay.
Yes.
So the next thing after this, we have practiced that if we use a simplest circuit to light up a lamp, we will use a lamp, we will use a cell, we will use these brown wire, and we will use a lamp. Got it? So this is a simplest circuit to light up a lamp. Is that okay? The circuit which we have drawn is the
Yes.
simplest one.
Yes.
We have not even used the like a switch. So in this simplest circuit, we have used three things: the cell, the lamp, the wire. The cell has the chemical energy and it converts it into electrical energy. The lamps we use that it converts that electrical energy into light and heat, right? Into light and heat. Okay, into light and heat. And what wires do? Wires transfer the energy, provides the free electron which can transfer the energy from the cell to the lamp. Got it?
Yes.
From the okay. So the next is voltage. So what happened? Look at the as the electrons are flowing, what's happening? So battery provides them energy. That's what the cell is for. Cell provides them energy. They flow in this wire, wire, and reaches the lamp. When they reaches the lamp, lamp only consumes their electrical energy, not the charges. Lamp only consumes the electrical energy, not the charges. So what happened? The red thing in the circle is a bunch of electrons, which red shows that they are energetic. So as they flow in the wire, nothing happens to their energy. But as they flow through the lamp consumes their energy, radiate the red energy out as light and heat, and they left with just electrons, right? Now these blue electrons don't have any energy because the lamp has radiated that energy out, so they go back to the positive terminal of the cell. So what cells do? Cell again transfer the energy to the charges, to that 1 coulomb of charge. So 1 coulomb of charge means per unit charge. So the energy transferred per unit charge, whether to or by, that energy transferred per unit charge is called voltage. It doesn't matter it's to or it's by. If energy transferred per unit charge we are discussing, it's the voltage, it will be measured in volts. But in the cell, the difference is that energy is transferred to per unit charge, and in the lamp, that energy is transferred by per unit charge. So the energy we supply to the charges use that energy to go and make a complete round trip. So the energy transferred to per unit charge so that they can make a complete round trip. That's the reason why electron keep moving. As long as the cell provides that energy, the electron keeps moving in the circuit. So that energy transferred per unit charge is called electromotive force, which electrons use to complete a round trip. But if we just talk about energy transferred by the charge, so charge loses the energy. So the energy of the charge get dropped. So we call it potential drop. Is that right? And after that, we practice current, which is the rate of flow of charge. So rate of flow of charge is how much charge flow per unit time. So we write it as charge flow Q over the time T, is right? So voltage is V, which is equal to work done per unit charge. Remember, in electricity topic, we are not going to use E to represent energy. We are going to use W to represent energy, because energy is the same thing as work done. Okay, why we not use E? Because we have to use E for electric field, we have to use E for the EMF. So if we use E here, it will be a confusion whether it's the electromotive force or the energy. Got it? So that's why we use the W symbol. Is that right? So that's a brief review of what we have practiced. You can, I have recorded the lecture. I will upload it in a moment. So if you want to have a detailed look at how we discuss the things, you can check the lecture later on. Okay. So is there any question from what we have practiced today? Okay, so that's it for today. So thank you. Have a nice day. Allah Hafiz.
Allah Hafiz.